Good morning. In this lecture video, in continuation of previous video, I'm going to explain serial in parallel out shift registers as we discussed in the previous video. Serial in serial out register. So now serial in parallel out register. See, this is the configuration of serial in parallel out register. See, it is very similar to a previous serial in serial out register. Only the difference is we are taking the individual output to the output terminal. We connected Q0 to output terminal QA, Q1 to output terminal QB, and Q2 to QC, and Q3 to QD. And these we call a parallel data. Parallel data. Remaining connection as it is same as the previous. So this is the serial data in that will be applied to input to the leftmost. So let's verify the operation. Again, consider the same example 1101. So here also, since it is a left shift, we need to transfer LSB first. Let's see the function table. Clock signal, serial data in, and content of flip-flops. So let's see initial. This is the initial content. Now set serial data in 1. When the clock pulse occurs, this one will be loaded into Q0, and Q0 value will be shifted to Q1, Q1 to Q2, and Q2 to Q3. And second bit here you set 0. So once the second pulse occurs, this 0 is loaded into Q0, and the remaining bits are shifted one bit position to the right. And third bit 1, and 1 will be loaded here on occurrence of a third clock pulse, and the data get shifted. Clear na? And the fourth bit, that is 1, again 1 is loaded here, and the data get shifted. Clear na? So now data is loaded. That means 1101 is loaded. See, as soon as the data is loaded, since we connected output of a flip-flop to an output terminal, they are available on the output terminal. Data is available on output terminal. So only we need to load the data. As soon as loading is completed, the data is available on output terminal. So for in, we need 4 clock pulses are required. For out, not required. So together we require only 4 clock pulses. As you know, to perform serial in serial out operation for 4-bit register, we need 8 clock pulses. Here for serial in parallel out, we need only 4 clock pulses. Clear now? Yeah. Next one is parallel in parallel out register, PIPO. So we are loading the data parallelly, and we are retrieving the data parallelly. So again, it is very simple. For 4-bit, we use 4 D flip-flops. See, in flip-flop inputs are connected to parallel data in. IA is connected to D0, IB is connected to D1, IC to D2, and ID to D3. So we call these are parallel data in. Whatever the data we are loading, we need to set on these pins. And out, for out, Q0 connected to QA, Q1 to QB, Q2 to QC, and Q3 to QD. And these are the parallel data out pins. Okay, so let's see function table. So here we added parallel inputs. In the previous 2 registers, serial data in, but here is parallel data in, or we can say parallel inputs. That's IA, IB, IC, ID. Let's see initially. So this is the content. Correct? So now if you want to load 0110, that we are setting on IA, IB, IC, and ID pins. Once the clock pulse occurs, that will be loaded into registers. Same data. IA data is copied to QA, IB copied to QB, and IC copied to QC, and ID value copied to QD. Only one pulse required. Right? So suppose if you want to store uh, 1001, when the second pulse occurs, these 4 bits are loaded into flip-flops and they are available on outputs. And for suppose next we need to load 0010, that will be loaded here. Okay. Again, if you want to store 1100, that will be loaded here. That means whatever the data we need to load, that we are setting on parallel inputs. Once the clock pulse occurs, the whole data will be loaded. As I said, no, this is a parallel data transfer. We require a number of lines equal to the number of data bits to be transferred. So this is about parallel in, parallel out, shift register. Okay, fine. So only one pulse is required. So this is the uh, timing diagram. Timing diagram. See, this is the clock pulse. This is the clock pulse, and here it is called positive edge. Since the transition is from 0 to 1, and this is called negative edge. Since the transition from 1 to 0. Okay, so this is positive edge, negative edge, positive edge, negative edge. So as we observed in the previous diagram, flip-flops are positive edge triggered. Positive edge triggered. Correct? So say these are the parallel data inputs IA, IB, IC and ID. Correct? So initially it is 0, 1, 1, 0. So same thing is loaded into available on output 0, 1, 1, 0. Now if you want to load this is the previous value which is stored here. Now when the clock pulse occurs, if you want to load 1, 0, 1, 1, I mean we made IA 1, IB 0 and IC 1 previous as it is previous and ID 1. Correct? When the positive edge occurs, see this is the positive edge, no? So QA loaded with the IA value, that is 1. That is 1. Okay. Becomes QA becomes 1 and QD becomes a 0 since IB value is 0. And QC previously 1, now it maintains the same thing because again QC IC is 1. Okay, na? And QD becomes 1 because ID is 1. Clear na? So now if you want to load a for all zeros, so make IA 0, IB already 0, it maintains the same, and IC 0 and ID 0. So with this positive edge, QA becomes 0, QB already 0, so maintains the same, and QC becomes 0 and QD becomes a 0. Clear na? So whatever the data we are loading, we do the changes on parallel inputs. Once the positive edge occurs, that will be loaded into output terminals. I mean QA, QB, QC, QD. So first it is loaded into flip-flop, and from since the flip-flop outputs are connected to output terminal, so that the data is available on output terminal. So preferably we use timing diagram to describe the behavior of terminal behavior of sequential circuit. So register is also a sequential circuit because it is made up of flip-flops, and flip-flop is again a sequential circuit. So why flip-flop is sequential circuit? Since feedback is connected from output to input. Clear? So this is about the registers. Next we'll see serial parallel in serial out, shift unidirectional shift register, parallel in serial out. So this is the configuration. Clear na? See here again 4 flip-flops, D0, D1, D2, D3. See little bit circuit is added. See this is the part of the circuit. It consists of OR gate to AND gate, OR gate to AND gate, in OR gate to AND gate. Okay. Output of OR gate is connected to inputs to the flip-flops. Inputs to the flip-flops. Correct? And observe here we use one control signal, that is load bar shift. Here operation is controlled by load bar shift line. Okay. See here this is connected to, I mean uncomplemented. This line uncomplemented is connected to upper AND gates. Uncomplement line is connected to upper AND gate. One input of upper AND gate. Correct? Yeah. And its complemented line. Its complemented line is connected to one input of lower AND gate. One inputs of lower AND gate. Correct? So uncomplemented control line is connected to one input of upper AND gate, and its complemented is connected to one input of lower AND gate. And to the upper AND gate, to the first one, which corresponds to the leftmost one, D naught, serial data in is connected. And second input of upper AND gate, previous output. Here second input of upper AND gate, previous output. Again here also previous. That means it becomes a cascade connection. Correct? And second input of lower AND gate is connected to parallel inputs IA and here IA. That is second input of lower AND gates are connected to parallel inputs. That means it performs parallel load. So that means whenever it is 0, it performs load operation, because see, this 0 is connected to upper AND gate, no, right? So upper AND gates are disabled. I mean, it ignores the serial data in here. Output is 0. Again, it ignores previous data. Output is 0, because one input of the AND gate is 0. So whatever may be other input, output is 0. Correct? And its complement, that is 1. 1 is connected to lower one input of lower AND gate. And its output is depends on other input, that is IA. So IA will be copied to one input of OR gate. Okay, and other input is 0, no? So if one input of OR gate is 0, output of OR gate is same as other input. So either other input is IA. Which is transferred to lower AND gate. Similarly here, other input of OR gate is output of AND gate. So output of AND gate is IB. So IB will be transferred to, connected to D1. Similarly here, IC is connected to D2 and ID is connected to D3. So it performs parallel load operation. Clear na? And for shift operation, the control signal should be 1. Remember here. So it is 0 means here it is load bar active low. It enables. Okay, it disables. It is active I. Here load bar means if it is 1, disable. Shift is active I, so it is enabled. So flip-flop becomes a cascade connection. As I said, no. Here it is 1, no. 1 is connected to upper AND gate, and its complement 0 is connected to lower AND gate. So lower AND gates are disabled. Output is a 0. Okay, and upper AND gates passes the output same as the other input. Here other input is serial data in, and that will be available to D0. Here second input of upper AND gate is QA, that will be transferred to D, and similarly QB will be transferred to D2 and QC will be transferred to D3. So it performs parallel in, serial out. To perform parallel in, we should make control input 0, parallel load, and for shift operation, that is serial out, we should make control input 1. Clear now? So functions are unidirectional shift register provides serial output. Clear now? Yeah. So next video I'm going to explain bidirectional shift register. So thank you. I will continue in the next video.